Hello, welcome to session number 2 in the series System Design. My name is Anurag Nigam, and we are looking at using system view for your system level simulation. And what I'm going to talk to you about is today, how do you generate QAM signals or quadrature amplitude modulation signals? And I'm going to use something like I'm going to generate something like 5G signals, but they are very simplified approach to generating 5G signals. What in essence I'm generating is a QAM 256. But let me explain you what is a QAM, right? So QAM or quadrature amplitude modulation, right? What it does is, let's say we have a phasor representation of a signal. So a phasor can be represented by an amplitude, right, and a phase, right? So that's a phasor representation. So this is a polar representation, right? So I have an amplitude and a phase which I'm representing. Now the same thing can be split into something called IQ signals, right? So I can say I plus JQ, right? So I can have this same signal represented as a IQ signal. So in that case, what will happen is I'm looking at the rectangular coordinate system like this. So this one, let's say, is the Q, this one is the I. So I have a this thing representation. Now what am I going to do? I am going to transmit two signals, I and Q, using a carrier. So I can say that I sine of omega t, and then I can say Q cos of omega t. Now these two signals are orthogonal to each other, so if I add them and then I'm going to transmit them, so when I receive them I am going to just mix it with, let's say, sine wave. So in this case it is going to be this signal which I have received, and I am going to mix this with a sine wave. So when I mix this with sine wave, this component goes to 0, right? And what I'm left with is half of I if I do the low pass filtering, because I'm going to get a second harmonic here which is plus half of sine of twice of omega t, right? So this low pass filtering will get rid of this component, so I'm left with only this component. So I would have recovered I. Similarly, if I was to mix this signal with Q, right, with Q, if I mix this signal, make this signal with cos of omega t, sorry, so then I'm going to get half of Q plus half of, sorry, here it should be cos of omega t, okay. Sine square theta is 1 plus cos 2 theta by 2, right? So similarly here it will be half of okay, I component will be also there, here Q component, half of cos of twice of omega t, right? So this portion will filter out, so this portion would be gone, this portion will be gone, and I would have recovered Q signal. Okay, so this is how QAM modulation works. Now what do I do to generate this QAM modulation in system view? Okay, so I'm going to generate a QAM 256 and see what are the limitations on filtering and linearity, right? So I'm going to generate QAM 256. What it means is the following. Okay, I'll explain you with QAM 16 what it means. What it means is I am going to group, so I'm looking at QAM 16. Okay, so I'm going to group 4 bits. Let's say this is a random bit stream, right? So this is a random bit stream. Okay, so I can bunch these as 4 bits, right? So I'm bunching this as 4 bits. Now this represents one symbol. Okay, so there's something called a sample rate, and then there is something called a symbol rate. So symbol rate in this case is going to be equal to sample rate by 4, because I have clubbed 4 bits to make one symbol, right? So once I have done this, okay, let me see if I'm recording it. Okay, fine. So Okay, so once I have done this, okay, what I do, I take a symbol and I am going to represent this symbol by a particular amplitude and phase information. So let me just make it symmetric. So I'm going to look at amplitude information and phase information, and I have divided this phasor, or rather I divided this coordinate system. Okay, just 1 second. Okay, so I have divided this coordinate system into 16 bins. Okay, and these are usually equispaced bins. Okay, so now this is referred to as constellation, right? So now there are 16 bins in here. Now each bin basically has a unique amplitude and a unique phase, right? So you pick up any one of them, unique amplitude and unique phase. So in this QAM 16, how many amplitudes am I going to see? I'm going to see 3 amplitudes, A1, A2, A3. So basically this one is 1 amplitude, this one is 1 amplitude, and this one is 1 amplitude. 3 amplitudes I'm going to see, and I'm going to see 16 phases. An amplitude phase pair uniquely defines a symbol. Now I can allocate these symbols to be according to what is called as Gray's code. Now why do I do a gray code is because in gray code, for example, let's say 4 bits, let's say start with this one, then the next one I have is this one, and the next one I have is this one, and the next one I have is this one. So at any point of time I'm going to change only 1 bit. So that means that I'm going to jump basically just 1 bin. Okay, so well, there can be different arrangements, not just gray. There can be different arrangements of how do you allocate this symbols to these bins, right? And that allocation also depends on the statistics of this signal, right? And we can come up with a certain coding which will result in a lower peak to average ratio. Okay, PAPR, or it is also known as crest factor. Okay, so all that research goes into lowering down the peak to average ratio so that my system linearity constraints are relaxed, right? So that's there. So we will come to this later on, or in a number of sessions we will see this. Okay, so the idea is to minimize PAPR when I do some kind of a coding here. Okay, now this is with QAM 16. QAM 256 is going to have 256 such bins. Okay, now these extents which you see here, these extents are the supply voltage. Okay, so now if you want to squeeze in more bins, that means that you have got to reduce the spacing between these bins. Okay, so these are the spacing between the bins, right? So if you squeeze in more symbols, or more you say more higher QAM, that means you are squeezing in more bins in this constellation, and that will mean that the two symbols are going to be closer to each other. Now what is going to happen is the following. Okay, let's say I have this constellation, right, and I am going to transmit these guys. Okay, so these are the different bins which I'm transmitting. Okay, so 16 of them, but I'm receiving them all over the place. For this one maybe I'm receiving like this. Okay, so I'm receiving like symbols which are all over the place around the ideal one which I'm expecting. Okay, so what I received is the red one, and what I'm transmitting is the blue one. Now this may be a result of what happens to the signal, what kind of noise it picks up and stuff like that. But besides that, this also depends on what you call filtering. Okay, so what is the procedure? Procedure is I take the random bits. So I take the random bits, and then I'm going to give this to some kind of a gray or any kind of an encoder, which is going to assign these symbols to this the bin in the constellation. And the output of the gray encoder I'm going to give to mapper, which is going to map this to your I and Q signals, right? So it is going to give it to I and Q signals, right? So beyond mapper, okay, we have got 16 bins, and this is like, instead of one signal you have got two signals, or rather you can say it's a complex signal, or it has got two components, I and Q components, and these components can be transmitted as is. But then there is an issue. If your waveform is a square wave, for example, these I and Q values are going to randomly miss, they're going to abruptly change, and so abrupt changes causes, so any abrupt change in time domain would be expanding in the frequency domain. So that is the nature of FFT. Okay, so, or the nature of two domains. If you something is localized in time domain, for example this edge is localized in time domain, to represent this edge I will need more frequency components if this edge is sharp. If this edge is not sharp, for example, if this edge is not sharp, then I don't need that many frequency components, right? So the bandwidth is a issue here. So if you want to minimize the bandwidth, you would have to low pass filter this out. Okay, so when you do a low pass filter, this edge becomes very important, right? And that basically depends on the order of the filter, right? The sharpness of the cutoff. So if I have some kind of a filter here, right? If I have some kind of a raised cosine filter, for example, why raised cosine filter? Because raised cosine filter will give you the minimum bandwidth. Okay, so there are three things in this raised cosine filter. What is this fall off? Okay, this fall off can be approximated, or roll off can be approximated by certain excess bandwidth. Okay, so you have excess bandwidth, and in this case it becomes stringent to have a very low excess bandwidth of the order of, let's say, 2% or something. In a typical system, this may be very, you can have something like 35% excess bandwidth, but when it comes to a higher QAM, this excess bandwidth is something which becomes very important. Second, this fall off becomes important. So I have this window, I can approximate this window as a rectangular. I can represent this as a Hahn window. I can represent this as a Hamming window. I can represent this as a flat top window. Okay, so various windowing is possible here. And second thing is I can do frequency equalization. So what it means is the following. Let's say if I am transmitting this and this goes through some form of a system where some of the frequencies are favored versus some are not. Let's say high frequencies are favored, then what is going to happen? Then this is going to happen. So basically what means is high frequency components basically are dominated by over the low frequency components. Now if the same thing is done low pass filtering, then what can happen is when you transmit it, then these edges is going to become fine, right? Not going to be so sharp. So this is low pass filter. Now if I want to enhance the higher frequencies, I can do some form of a pulse equalization. Okay, so this pulse equalization also becomes important. Okay, now pulse equalization, so first thing is the excess bandwidth, second is the window nature, third is the pulse equalization. Now if I do a pulse equalization, I might have a window which is like this. So there is certain frequencies which are enhanced, and then there is a roll off. Okay, so this is these are become important when the QAM goes higher, because all these things are what they are going to do is they are going to take your symbol and they are going to add this randomness to this, right? Because you have got something which is not exactly what you want, but this is just why do you do it? You don't want it, but why do you do it? To conserve the bandwidth, right? So that's why you are doing a filtering. So in filter, things which are important is access bandwidth, the nature of the window, and the form of equalization. And the third thing which is important is the roll off. Okay, so roll off nature, which is this roll off nature, this can be you know uh, some kind of a square root, right? So that can be a nature of roll off. It can be different nature of roll off which you can define in a filter. So filtering becomes very important when you go to higher and higher QAM, right? The next thing which becomes important is the linearity, okay, of the system, and we will cover linearity a lot later on, but right now we are just looking at a source, right? Okay, so having said that, so what are we going to do? We are going to have first we are going to have a random bit generator. So I'm going to have a random bits generator. Second thing is I'm going to put this through a certain encoder, which can be a simplified form of just a gray encoder, right? Third thing I'm going to do is I'm going to have a mapper. Okay, so logically this is what is happening, and then the output of the mapper is basically going to be filtered, right? So this is going to be filtered, and this filtered output is going to be given to IQ modulator, sorry, with a carrier frequency, and its output is going to be transmit. So this IQ modulator is nothing but it is doing this action. It is taking I modulating with sine and Q modulating with cos, and then it is just summing this up, right? Now this is going to be, let's say, Q, and then this you can do a reverse fashion also. You can do I with cos and Q with sine. So this possibility is also there, and this will be called Q quad or quadrature of that. So this this guy IQ modulator gives you two outputs. One is the quad output, and it's the Q output. So I'm interested only the Q output. If I do some complex envelope processing, I can involve quad also, right? But right now, for simplicity, I'm just going to use Q as the output, and then I'm going to look at Constellation here. So let's get started on this one. So I'm going to put this aside. Okay, so I have a blank workspace which is open. I'm going to just rename this. So I'm going to say save. Let me see if I'm recording. I might be talking just to myself. No, I'm recording. Fine. So what I'm going to do is I'm going to save this blank one as, let's say, QAM test. Okay, so I'm just generating a source which is going to be a QAM anything, right? You can also do a M array. So all things are handled in system view by just one modulator. Okay, so I'll show you that. Okay, so I'm going to first rename this and call this as QAM source, right? And then here I am going to rename this one also. Say response QAM. So that's the name of my analysis, response QAM. And here I can change this to refer to the design here, and here my sampling rate is, let's say, 11 megabits per second, and I think that's it, and automatic recalculation. Okay, so right now there is an empty data set. There is a warning because there's nothing in my schematic. Okay, so let's put something into the schematic. Let me move this out of the way. Okay, so as we discussed in session 1, there is a part selector here, and I want some random bits. So I'll just type here bits. So I'm going to filter by bits, and this one which I pick up is a random bit. Okay, so in this case I can choose random bits here. Now what is the issue with this? So let's see what is the issue of doing this. So let's say I pick up a sync. Okay, and I'm going to see what kind of random bits it's going to generate. Again, let me tell you, the sample rate over here the sample rate over here is basically the bit rate. So do not confuse this with the sample rate or oversampling of the bits. So oversampling is adjusted in my interpolation in the filter, okay, and then it is taken care on the demodulation side by the decimation factor. So oversampling and decimation, or interpolation decimation, that's how I'm going to handle the sampling per bit, samples per bit. But here the sample rate is the bit rate. Okay, fine. So I have the random bits here, okay, and let's see its response. Let's say add to graph. Okay, I can zoom into any. Okay, so these are the random bits which are being generated, right? And if I was to recalculate this, so these bits are changing. You see, every recalculation is going to change the bits. Now let's say if I want to compare one calculation against the other calculation, so I have to compare apples to apples. So if there is a random source in here like this one, it is going to change. So basically the response is going to change on every calculation, right? And if you do not want that, what you do is you go in here and change the model to PRBS, and that's it. And now if you do this calculation again and look at its representation, every time you do a calculation, nothing is going to change here. Now this is for one source. Let's say if I have noise, right, the noise is random, and I want to keep, for every calculation I want to keep the noise also fixed, right? It's a random process. Now in that case I have multiple random sources here. Now in that case what's going to happen is I have another option to do this. Other option is I go to this data flow analysis, go to options, and says repeatable random sequences. So if this is checked, right, irrespective of whether this one is what kind of model, let's say it is random bits, okay, now this is random bits on the local level, okay, this is going to generate random bits, but the simulator is going to force it to keep it same from calculation to calculation, right? So here if I was to look at this, okay, so now you see this, and if I was to recalculate this, it didn't change. Even if the bits are random here, right, the graph is not changing from calculation to calculation, right? So if you want to set this at the global level, you will set this inside the analysis here, and if you want to set it at the local level, you are going to set it as a different model for this random bit generation here, right? So I'm going to choose this one, because let's say if I want to put noise which varies, right? So this is there. Now also this is going to be constant across calculations. Okay, so we are all set with this. So I hope I explained you what that model is. Now I want to take this and put it inside a gray encoder. So I'm going to take a gray encoder, and you can have a different encoding scheme which you can yourself write, but this is something which is the most simple one. So in this gray encoder I'm going to, let's say, 8 bits, so I'm targeting 256 QAM for 5G. So I have got 8 bits in here, right? So it is going to take these random bits of ones and zeros and bunch them into symbols, and each symbol is going to have 8 bits, right? So this is very simple. And then you are going to have a mapper. So this is going to do a IQ generation. This is a function of an IQ modulator actually. So if I go to mapper, and what that is going to be a very simple mux, right? So let me just do undo. Okay, mapper. Okay, so that mapper goes in here, and this is a QPSK mapper. Okay, it's nothing special in here. It's just going to map the symbols to the respective bins, right? And its output is going to be complex because it has got two components, I and Q, right? So its output is going to be complex, and this is a numeric sync, right? So here it makes sense to take this complex and split it into rectangular components, right? So here I'm going to go to complex 2, complex to rectangular. Okay, search for this component. So complex signal is converted to two real signals, which is rectangular components to that complex signal. Okay, so now here I have got these two signals. Now I can put in here sync, right? And I can put here two numeric sinks here, 1 and 2. Okay, so I have got two numeric sinks here, which are going to read I and Q signal. And mind you that this is not filtered, so you will see all the sharp notches and things like that. So let me just do this, and let's just calculate this. So I have got S1 and S2. So let's go and here and add a graph. Okay, so I'm going to say right click, add a graph. Okay, so I'm going to look at what it looks like if I plot y versus x, which means if I plot S1 versus S2. So remember in my remember in here, so remember in here, okay, I told you that we are mapping this to I and Q. So these are I and Q components. Okay, so these are your I and Q components. So what comes out of complex to rectangular are these I and Q. And if I want to look at this constellation, one way to do this is plot I versus Q or Y versus X, right? So this is what I'm going to do, right? Sorry. Okay, so that's what I'm going to do. Sorry about this. Okay, so Y versus X. So let's say S2 versus S1. And say okay. Hang on a second. 8-bit QPSK. 8. Okay, here you have to put in QAM 256. So now it's going to map that, and then it's going to give you I and Q. So let me just run this again and look at its output here. So you see here all of them are connected, right? So I want to look at the non-connected ones, right? So so let me just change this to -2, just change the scale and change this to -2. It's 2. Okay, it took a marker here. Okay, anyways, so over in here there is this entire constellation of 256 symbols, and they are all connected out. So let's see if I can change the graph. Change the graph. This is rectangular. I just don't want to connect them. I want to just change the nature of it. I don't want to connect them, right? So there may be another graph, maybe, which is unconnected. Okay, trajectory will do it. Let's see that. Trajectory, no data is available. Clear mode. Constellation, no data available, because this is not a complex envelope, so that's why it's not available. Can't change the the type nature of the graph. But anyways, so what I'm going to try explaining you is the following. Okay, what's happening is all your 256 bins are here, and then these bins are plotted out here. So this is just a connected graph. That's why you see so many lines running and you are not able to see the constellation. So let's change this a little bit. What I can do here is I can take a spectrum analyzer. Okay, so look for a spectrum analyzer. Okay, so that's a spectrum analyzer, and this one I can read it over here, but this is a complex data, not an envelope data. So change the model to complex, and now if you connect this, you will be able to see the spectrum. So let's see now. Compute, and I can go to graph, add graph, and add graph, and here now I can look at spectrum. Here's S3 is available. Okay, so this is a spectrum which is going to be 11 megabits, but then this is centered around 0. So this is a complex number, because this is why this is centered around 0 is because this is no envelope, there is no carrier frequency here. That's why it is. So later I'm going to use this. Now the order of business here is, so let me just get rid of this graph. Okay, I need to insert two filters in here, so I'm going to design these filters. So I'm going to go to filter, designer, or filter design. Okay, look for this component, and there it is. So I'm going to make a new design, and I am going to say okay, and just drag it over here. So this is I'm going to design a FIR filter. So I'm going to double click that. I'm going to choose a raised cosine filter, and here I'm going to put sampling rate, which comes from your controller, data flow controller. So that's your sampling rate, and the symbol rate is 1/8 of that, because I'm clubbing 8 bits to make 8 bits to make one symbol. So that's get divided by 8, and this is the roll off, and this is the excess bandwidth. So as I told you, excess bandwidth becomes important, so let's keep it 2. Then the nature of roll off is, let's say, square root. Pulse equalization I'm not giving for now. Length of the filter I'm going to choose using number of taps, and here I'm going to put a length of the filter is 1024 or 1025, an odd number. And then here is the windowing. Here I can choose to be a Hamming window. So just one second, instead of a rectangular window, I'm going to use a Hamming window. And then I am going to put an interpolation of 32, let's say 32, and yes, and then pulse equalization also want to see, and say design. Okay, so that's the filter here with its impulse response, right? So I'm done with the filter design. I'm going to copy this filter, Control C, Control V, and I'm going to place it here. Okay. Okay, and I don't need the second sync. I'll tell you what I'll do. I'll just copy this, Control C, Control V, right? And so I'm going to filter out the signal as we have discussed, right, to conserve the bandwidth. Okay, and after this I need to give this to a modulator. So if I give this to a modulator, and this is a modulator I'm going to use. Okay, so this modulator is a common thing, right? It's for various modulation techniques, and this is just a IQ modulation, right? So I just choose input type as IQ, and the carrier frequency is 2.45 gigahertz, for example. So this is like, or let's say 3.5 gigahertz. That's your Ymax sub 6 gigahertz. Okay, 3.5 gigahertz. Okay, so you have this modulation, and then there are two components which are coming out. One is the quad component, as I discussed, and one is just the out. So I'm just going to use the out because I'm not doing any envelope processing beyond this using two of them. I'm just using one of them, and here I can just take this bits and look at it, and then also I can put here a spectrum analyzer to see the spectrum. Okay, and here I don't have to do any settings in here, so we are all set. So what did I do here? I took the random bits, put it into a gray encoder, bunched them as 8 bits per symbol, then mapped those symbols to IQ, and the output of IQ I've converted. It's a complex number, so I'm looking at I and Q rectangular components. I'm filtering them out using a race cosine filter, giving the filtered output to a modulator, frequency modulator, IQ modulator, and then the output of IQ modulator I can collect it as S1, and then also and a numeric sink, and then also look at this spectrum. So this is done. So let's simulate this. So once I'm done with the simulation, let's look at some of the graphs. So I'm going to add let's say a graph to look at this output spectrum, and in this case the spectrum comes as S2 power spectrum. Okay, and say okay. So this is your 11 megahertz bandwidth, basically what's your sample rate, you can see here. Okay, so this is around 3.5 gigahertz, and this is your modulated signal. Now I can also look at the constellation, so I can go to add graph, and here I would go to constellation S1, and here I need to add it some things. So if I just do this S1, this is not going to be correct. Why? Because there are the sampling rate I have to specify. Okay, otherwise it will be all over the place. So here I have an interpolation of 32, so basically I have 32 samples per bit, and then there is a startup delay which should be half the filter length, so it is 1024, so it will be 512. So this will be the filter length, and say okay, and say okay. So once I'm done with this, so this is what you get. Let me put the axes right. So let's say this is -2 to 2, so that you see what you have seen earlier. Okay, so what has happened is I have got this QAM 256, but if you remember, this is going to happen. This is because of the filtering here, the excess bandwidth, the roll off, the pulse equalization. So all these things contribute, the nature of the window, all this cause this to not be exactly these blue dots. They are going to be rather red dots, and in this constellation none of the effects of non-linearity or any other effects like noise, they are not into this. So right now you are looking at a pure source with a certain filtering, right? So this is what you're going to transmit, QAM 256, and then it would go through your transmit receive chain, and it will also go through your channel, and these are going to add all your noises. They are going to skew this constellation, they are going to rotate this constellation, they are going to when things go to compression, a non-linearity, they are going to move these bins all over the place, in the sense that you can see the effect once you put it through the chain, and I'll do that later on. Okay, so what you have received is 256 bins in that constellation. Now if I want to see the ideal, so the ideal case would be I take this filter and remove the roll off. So I'd say I don't want to show it a roll off, right? And then you should get exact blue dots, what you are seeing, right? So if I simulate this, okay, this graph has an issue, so let's just delete this graph. This is from the previous simulations. Okay, so the simulation is done, and let's look at that graph. So that graph this is what you get without filtering, right? So without filtering, you'll see those blue dots. So if I go here, those blue dots are basically these dots here. There's no error in here. Everything looks like ideal here. right? So this is all ideal. Now if I was to put certain roll off onto the filter edge, then I'm going to get some distortion in where I'm sampling it, right? So that's what you're going to see with the excess bandwidth. So what I do is I go here, put back the roll off, yes, and put back the roll off here, yes, and say okay, and just recalculate this, and you see that they are kind of, again, they are kind of scattered around now. This is not what you get with the ideal case, right? So this is a QAM 256 which I have generated. This is at 2. So if I look at the spectrum, this is at 3.5 gigahertz, and this I'm going to put into a channel beyond this, or into a transmitter, and then a channel, and then a receiver, and then demodulate this out. So in the next section I will cover the demodulation, and after that I will look at the channel modeling and stuff like that, right? Now this is exactly not 5G. Okay, this is just a QAM 256. What is a MIMO or a massive MIMO is basically you take a high-speed stream of data, ones and zeros, split it into sub streams which are going to be slower, and then you are going to modulate carriers with those substreams, and these substreams are uncorrelated substreams. The data is uncorrelated. So when you modulate these carriers or subcarriers with these substreams and transmit it, the entire envelope is going to see all kinds of noises and channel related distortions and things like that. Once you receive it, okay, once you receive it and you separate the subchannels, right, then there is a lot of correlated information between subcarriers, and that correlated information is the channel estimation or the noise, stuff like that. So you do not have to have a explicit channel estimation here. If you can separate out using some form of filtering, right, you can separate out the correlated information from the channels, and then you can basically subtract it from each subcarrier, and you have a noise-free reception. So that brings the ruggedness to the MIMO system. And in MIMO systems, these channels have to be orthogonal, in the sense they should not have any correlated information. That's what you mean by orthogonal. Otherwise you'll be confused between what is channel estimation and what is the signal, right? So you have to have these uncorrelated. Now when it comes to massive MIMO, as you do in 5G, the number of subcarrier channels are more, number of sub channels are more, and that means that there is more randomness to it. Now this relaxes certain constraint on orthogonality of these sub channels. They need not be exactly orthogonal. So that is basically the essence of 5G, where you can have non-orthogonal channels and still have a high data rate, you still have very good noise immunity, right? So in 4G you used to have all the subcarrier, all the subchannels to be orthogonal, but in massive MIMO, because of the huge number of channels, statistically the correlation, okay, effects are less, so you can relax the orthogonality, and that's why the channel capacity of 5G is much more than that of 4G. That's the basic difference between 5G and 4G. So we are going to explore that later on in the subsequent sessions. I am going to stop here. I have just shown you how to generate a QAM signal. Okay, thanks a lot. Thank you very much.